changes in more detail. We are now going to be studying enthalpy changes quite different to what you guys have already done in your IGCSE. Okay, now, first of all, let's quickly go over the basics, right? Let's quickly go over our basics and then let's go ahead and actually take a look at the information in this topic that you need to know. Now, to revise our basics, if you guys remember, we had studied that there are two types of reactions, right? We can have exothermic reactions and we can have endothermic reactions, right? This is something that you guys already know quite well. We're just going to go over it quickly. In an exothermic reaction, the temperature of the surroundings increases. Why? Because if you remember, you might have studied this, that in exothermic reaction, the energy released during bond making is greater than energy needed for bond breaking. So bond making, whenever I make a bond, I will be releasing energy. Whenever I am going to be making a bond, I'm going to be releasing energy. And whenever I'm going to be breaking a bond, I'm going to have to provide energy. So in exothermic reactions, I don't need to provide that much energy. The energy I need to break the bonds is not that much. But when the bonds will be made, the energy that will be released from the process is going to be much greater, right? Hence, our reaction is exothermic. When we talk about the surroundings, we are going to be talking about the solvent. For example, if it's in a solution, so the solution, the temperature of the solution will increase, or the temperature of the surrounding air will increase. Your test tube, your beaker, your equipment will get hotter, right? Your thermometer is going to get hotter. Then, of course, we can have endothermic reactions. Endothermic reactions are reactions where reactions that absorb energy from the surroundings, right? Reactions that absorb energy from the surroundings would be your endothermic reactions. And in this particular situation, the temperature of the surroundings would decrease, right? The temperature of the surroundings would decrease, and that's what we had studied. When we talk about our enthalpy change, okay? So what is enthalpy change? Heat energy exchange. The heat energy exchange between a reaction and the surroundings is enthalpy change. Enthalpy change is written down with a symbol of delta H. Enthalpy change can be calculated. If I want to calculate enthalpy change, so I can calculate it quite easily. I can take my enthalpy of the products and I can subtract the enthalpy of reactants from it. So if I do that, if I take the enthalpy of the products and I subtract the enthalpy of the reactants, I will be able to calculate my enthalpy change. Enthalpy change, the units for enthalpy change are generally, we use kilojoules per mole. That's the most common one. But you guys are going to see joules per mole as well in certain situations. So you will have to be really careful with your calculations. So enthalpy change, if you guys remember, if the value of enthalpy change is negative, right? If the value of enthalpy change is negative, that usually meant that we were dealing with an exothermic reaction. And if the value of enthalpy change was positive, that meant that we were dealing with an endothermic reaction. And now we can understand why, right? Now we can understand why exactly were we seeing it like that. Why is it that negative means exothermic? Negative means exothermic because if you guys take a look, I said enthalpy changes enthalpy of products minus enthalpy of reactants. So in an exothermic reaction, what does that mean? That means that the enthalpy of reactants is less and the enthalpy of the products is more, right? Sorry, I'm saying it the other way around. Enthalpy of the products is less and the enthalpy of the reactants is more. And if I make an energy diagram, you guys will see the same thing. In an exothermic reaction, what was it that we had studied? We had studied that the products will have a lower energy level and the reactants will have a higher energy level, right? So since your products have a lower energy level and your reactants have a higher energy level, what does that mean? That basically means that your when you will subtract them, when you will subtract the product and the reactant, you will end up getting an answer in negative. That's why negative enthalpy changes exothermic reaction. Okay, this is why negative enthalpy changes exothermic reaction, because I do product minus reactant. So since my product has a small value and the reactant has a higher value, so I end up seeing this kind of energy change, right? This would be my activation energy and this would be my enthalpy change. If I want to calculate enthalpy change, remember this, enthalpy change is always reactant minus product. Okay? And activation energy is always the energy that is going to be, we always, when you're labeling the arrow, we start from the reactant and we go to the top of the hump, right? The very top of our curve, we go to the very top of our curve. So if I go to the very top of my curve, that is going to be from the react to the top of my curve, that is going to be my activation energy. In an exothermic, this is for exothermic reaction. In an endothermic reaction, you will see that we end up getting a negative value, right? That's what you had studied, that we end up getting a positive value for our enthalpy change. So we had studied that if we get a positive value, we are going to end up seeing that we are going to have a endothermic reaction. Now we can understand why. Because in this particular scenario, what happens that our reactants are at a lower energy level and my products are at a higher energy level, right? So my products have a high energy and my reactants have a low energy. So when I subtract product minus reactant, I end up getting a positive answer. So as a result, a positive enthalpy change is associated with what? It is associated with a endothermic reaction. And in endothermic reaction, our labeling again is quite simple. Our labeling is like this. Our activation energy is always going to be from the reactant to the top of the curve, right? So this is my activation energy. Over here, if you're going to go ahead and take a look, if we're going to go ahead and we are going to take a look, product minus reactant is what? Is our enthalpy change. So this will be our enthalpy change, right? Now, this was everything that you guys probably already knew from before. This was just a revision of basic concepts that you had to have in your mind before we could actually talk about our topic. Now, when we talk about our enthalpy changes, you're going to see that when we talk about enthalpy change, we need to go over certain terminologies. Before you and I can actually discuss the topic of enthalpy change, and before you and I can actually talk about how to calculate enthalpy changes, we need to go over a few terminology. Enthalpy changes can be of different types, right? For example, we can have something that is known as standard enthalpy change of neutralization. What is standard enthalpy change of neutralization? What actually is it? Now, when we say standard enthalpy change of neutralization, standard means that I am talking about very specific conditions. Standard conditions mean that I am going to be dealing with standard conditions, which are what? Our atmosphere, our temperature. Our atmosphere, our pressure is going to be at 1 atmosphere, that's room pressure, and our temperature is always going to be at room temperature. So when I am measuring these enthalpy changes at standard conditions, that is 1 atmosphere or at 293 kelvins, right? Room temperature, that is standard conditions. Okay, so standard enthalpy change automatically means that I'm doing the experiment under standard conditions. Now, what actually is standard enthalpy change of neutralization? The definition is this. It is the enthalpy change when 1 mole of water is formed by the reaction of an acid with an alkali under standard conditions. And I told you guys what your standard conditions are, right? Your standard conditions are going to be that you are going to be at room temperature and pressure. So either the pressure is going to be 1 atmosphere or 101 kilopascal. If you want to write it down as Pascal, then it's 101 kilopascal. And if you want to write it down in the units of atmosphere, so it's 1 atmosphere. And it's going to be at room temperature, right? That's generally around 293 kelvins or 298 kelvins. So this is your standard conditions. Now, I will tell you guys something really important. In this topic, these definitions are very, very important. Not just because they will give you the definitions and they will say, oh, define this. They do. You will see a lot of questions, 2-mark questions, where they will simply say, tell us the definition of this, right? That's going to happen. But the main reason you guys need to make sure that you absolutely know what the definitions are is because you need these definitions for calculations. What do I mean? What do I mean when I say you need the definitions for calculations? You see how the question, how the definition says it is the enthalpy change when 1 mole of water is formed. It's really important. This 1 mole of water is extremely important. Why is this 1 mole of mole so important? Why am I emphasizing on it? Why am I saying this is so important? The reason I'm saying is that it's because it's going to affect your calculations. Okay. So when you guys are going to be doing your calculations, it will be up to you to see. This is really important. Why is it important? Because it's going to be up to, they will give you the value of standard enthalpy change. They will give you the value. It's up to you to look at your reaction and see if you're getting 1 mole of water or not. If in the reaction you're getting 2 moles of water, then you have to multiply the value by 2, right? The standard enthalpy change that they will give you in the exams will always be for 1 mole of water, right? And this will change for different definitions. There are different requirements. So for enthalpy change of neutralization, we need 1 mole of water. That's the requirement for this, right? Now, that means that if in the exam they give you the value for 1 mole of water, what does that mean? That means that you need to go ahead and make sure that you multiply the answer by 2, right? Because your equation is getting 2 moles of water. In your equation, you're making 2 moles of water. So if you're making 2 moles of water in your equation, you have to remember that you have to multiply your value by 2 because this is for only 1 mole of water. This value that is given to you is only for 1 mole of water. If I were to give you an example, right? You know how, let's take a very simple equation. Let's take hydrochloric acid. Let's take hydrochloric acid. Let's take HCl and then let's react it with sodium hydroxide. If I react HCl with sodium hydroxide, so we will get a salt and water. That's the acid-base reaction we have studied. Our salt is going to be sodium chloride, and we will end up getting 1 mole of water. So in this equation, the enthalpy change for this 1 mole of water being formed. The criteria, 1 mole is only for water, not for HCl, not for sodium hydroxide, water. I need to get 1 mole of water. What if I take sulfuric acid and I react it with sodium hydroxide? If I take sulfuric acid and I react with sodium hydroxide, the situation changes, right? If I take my sulfuric acid and I react it with sodium hydroxide, I will still get a salt and water. My salt will be sodium sulfate and my water will be H2O. But now if I balance the equation, what am I going to see? I'm going to end up seeing that I'm getting 2 moles of water. Since I'm getting 2 moles of water, so whatever the standard enthalpy change of neutralization is, I will have to multiply it by 2 to calculate the enthalpy change of this reaction. So if I want to calculate the enthalpy change of my second reaction where I'm using sulfuric acid, so I will have to multiply the enthalpy change of neutralization by 2 because I'm making 2 moles of water. That's why I'm saying these definitions are very important. Not just because they are going to help you answer your definition questions, which are really important because you can score full marks for answering them correctly. But they're also very important because if you don't remember these correctly, you will not multiply your values correctly and you will not get the correct answer, right? So this is the first definition that we had to go over. The second definition that we have to go over is another standard enthalpy change. But this time we're going to be talking about standard enthalpy change of solution. What is standard enthalpy change of solution when we're going to talk about it? So let's see. Standard enthalpy change of solution. Again, this is going to be under standard conditions. Our definition is that it is the enthalpy change when 1 mole of solute dissolves. When 1 mole of solute is dissolves in a solvent, to form an infinitely dilute solution under standard conditions. So standard conditions are the same as before. They will not change. Standard conditions are the same, that it has to be at room temperature and pressure. But this time, we need 1 mole of solute. Over there, we needed 1 mole of water. This time, we need to make sure that we have 1 mole of our solute. That's our requirement. We need to go ahead and make sure that we have 1 mole of the solute. That needs to be present. That means if 2 moles of solute are dissolving in the solvent, so that I will have to multiply the value by 2 to calculate the enthalpy change for that reaction, right? That's why we're spending so much time on these definitions, because if you don't remember the definitions correctly, it will 100% affect your answers. So if I want to calculate the enthalpy change of a reaction in which I have 2 moles of solute, I have to remember to multiply it by 2, right? Next, they're saying it's an infinitely dilute solution. What is an infinitely dilute solution? Infinitely dilute solution is a solution which is so dilute. It is so dilute that adding any more water won't change the enthalpy change anymore. Whatever my enthalpy change is, adding any more water to it will not bring any more changes. The enthalpy change value is not changing anymore. It has become constant. So when I dilute the solution so much, when I add so much water to the solution that it is not, the enthalpy change is no longer taking place, there is no more heat energy taking place, that is when you're going to be at an infinity dilute solution. An infinity dilute solution is going to be when 1 mole of any substance is dissolving in water, right? So that is in standard enthalpy change of solution. Similarly, we will have another type of enthalpy change. Another type of enthalpy change is again that you have in your syllabus is standard enthalpy change of atomization. What is standard enthalpy change of atomization? What are we talking about? Now, what actually is atomization? Let's start by discussing that first. So, standard enthalpy change standard enthalpy change of atomization is when is the enthalpy change, right? Is the enthalpy change when, now this is important, when 1 mole of gaseous atoms, when 1 mole of gaseous atom is formed from its elements, when one form of gaseous atom is formed from its element under standard conditions. Now, what does this even mean? What does that actually mean? What is all this? So, when we are going to go ahead and talk about it, it means this. I am taking, let's say, hydrogen gas. Okay. Let's say I'm taking hydrogen gas. Now, if I take hydrogen gas and that hydrogen gas is actually breaking down. So hydrogen gas has the formula of what? It has the formula of H2, right? So if I take my H2 and I break it down into atoms of hydrogen, gaseous atoms of hydrogen, that's going to be what? That's going to be my standard enthalpy change of atomization. But one small thing we have to add. One small thing I have to add is I have to balance it. The question, what does it say? Let's take a look at it very closely. The definition says that it has to be 1 mole of gaseous atoms. Okay, our product has to be 1 mole. Our atoms have to be 1 mole, which means if I'm balancing the equation, I will write down half H2. Similarly, if the formula or if the equation had 2 gaseous atoms, we would have to multiply the value given to you in the exam by 2, right? Similarly, this can be any element at all. We can have sodium. So if I take sodium and I turn it into sodium atom in the form of gas, that is enthalpy change of atomization. If I take my Cl2, half Cl2, and I turn it into chlorine molecules, Cl, that is going to be my enthalpy change of atomization, right? So standard enthalpy change of solution is when you make when 1 mole of a solute, so solute is the reactant, dissolves in a solution solvent to make an infinity dilute solution. Standard enthalpy change of atomization is when 1 mole of gaseous atom, this is the product now, is formed from its element under standard conditions. So as you can see over here, the definitions are changing, right? Who is going to be acting as the 1 mole? We don't know. Sometimes it's the product, sometimes it's the reactant. So it's really, really, really important that you guys make sure to learn the definitions very well. because these definitions not don't again I'll say you don't just need them for the purposes of doing your answering definitions, because you get a lot of questions about the definitions, but they're also really important because you need to know how to do your calculations. Is everything making sense so far? Does anybody have any questions on the topic? Is everything clear?
Yes.
Aruj, is
Yes,
everything clear
miss.
so far? Okay, all right. Now, if we continue on, then we have to go over our what other type of enthalpy changes do we have? So we another type of enthalpy change that you have to go in the syllabus is standard enthalpy change of hydration. What is standard enthalpy change of hydration? If you guys remember your topic of IGCSE, you must have studied about anhydrous salt. If you remember, we had studied that we can do an acid and base reaction and we can get a salt. That salt can be in the form of a solution. And if you want to get the salt, if I want to get a sample of the salt, I will have to perform crystallization. And in crystallization, we had studied that we heat the solution slowly. We heat it up slowly until we get the crystals, right? We had studied that we don't evaporate all the water, because if we evaporate all of the water, we will get anhydrous crystals. Crystals that have no water molecules attached to it, that have no water of crystallization. So, what is going to be standard enthalpy change of hydration, right? It is the enthalpy change when 1 mole of a hydrated salt. So 1 mole of hydrated salt means that the crystal with the water of crystallization in it. So 1 mole of hydrated salt is formed from 1 mole of anhydrous salt. So in this case, both of them are 1 mole, 1 mole. The hydrated salt also has to be 1 mole, and the anhydrous salt also has to be a 1 mole. And we do this under standard conditions. This would be our enthalpy change of hydration, right? If we go ahead and write down the equation, what would the equation look like? The equation would look like this. We have, for example, a crystal of sodium thiosulfate. So sodium thiosulfate is Na2S2O3. This is anhydrous. Okay, I have an anhydrous salt. I add water to it. And after adding water to it, it turns into a hydrated salt. It turns into crystals, right? So it turns into, it will have water of crystallization. So this would be your enthalpy change of hydration. This would be your enthalpy change of hydration. So again, in this, we have to pay attention to what? We have to go ahead and pay attention to the fact that we need 1 mole of hydrated salt is formed from 1 mole of anhydrous salt, right? These are the two definitions that we have to go ahead and actually points that we have to remember. Now, if we continue discussing, right? If we go ahead and we continue discussing the topic, another important definition that we have to go ahead and go over is our definition for yeah, I think we have, okay. Now that we have, so these are the different definitions that you have to go ahead and remember. Now, another important definitions that you have to know is something that is your enthalpy change of formula. formation. Okay. What is enthalpy change of formation? Enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. Let's talk about the definition itself and see if we can understand what they actually mean by it. So, let's say I am trying to make carbon dioxide. Okay. So, if I make 1 mole of carbon dioxide, okay, from its elements. So, what are the elements that are found in carbon dioxide? Carbon and oxygen. So, if I take carbon and I take oxygen and I combine the two of them to give me carbon dioxide, that is enthalpy change of formation. Now, there is a criteria. First criteria is that we need to make sure that we are making it from the elements. If I'm making carbon dioxide by some other reaction, for example, I have taken a carbonate and I'm reacting it with an acid, or if I'm reacting it with a base, whatever, if I'm producing carbon dioxide gas that way, that's not formation. For formation to occur, the reactants have to be elements. The second condition is that they have to be in their standard state. Meaning, what is the normal state of carbon? Carbon is normally a solid. Oxygen is normally a gas. So I have to take them in their standard state. Similarly, what if I want to make sodium hydroxide? Right? If I want to make sodium hydroxide, what do I need? I need sodium. I need the elements. I need sodium. What is the other element inside it? Hydrogen. What is another element inside it? Oxygen. And they all have to be in their standard state, meaning that sodium will have to be solid, hydrogen will have to be gas, and oxygen will have to be gas. And I need 1 mole of the substance. So that means I need 1 mole of sodium hydroxide. So when I'm balancing the equation, I will not balance sodium hydroxide. I won't add a 2 to the sodium hydroxide. Why? Because I want 1. So when I'm balancing my equation, I will write down half O2. I will write down half H2, right? This is standard enthalpy change of formation. Standard enthalpy change of formation is very important because you guys will see quite a lot of questions related to it. So that is another enthalpy change that you guys will be seeing quite a lot in your syllabus. After this, another enthalpy change that you guys are going to be seeing is going to be from its elements in their standard states. Okay, those are two important things we have to remember. All right. Another important thing that we have to remember is a definition about that is related to combustion. Okay, we call it enthalpy change of combustion. What is enthalpy change of combustion? So enthalpy change of combustion or standard enthalpy change of combustion is when you're going to go ahead and you're going to talk about it. So standard enthalpy change of your combustion is when 1 mole of a substance is burnt in excess oxygen, when 1 mole of a substance is burned in excess oxygen under standard conditions. That is enthalpy change of combustion. What do we mean by it? What I mean by it is quite simple. What I mean by it is that if I go ahead and I take my, if I go ahead and I take my carbon and I burn it in excess of oxygen, I'll get carbon dioxide. This will be standard, my standard enthalpy change of combustion. This will be my standard enthalpy change of combustion. If I have 1 mole of nitrogen, that 1 mole of nitrogen burns in oxygen to give me nitrogen dioxide. This is my enthalpy change of combustion, right? So this is what enthalpy change of combustion is. This is the symbol for enthalpy change of combustion. This is the symbol for standard enthalpy change of formation. This is the symbol for standard enthalpy change of hydration. This is the symbol for standard enthalpy change of neutralization. This is the symbol for standard enthalpy change of solution. And this is the symbol for standard enthalpy change of atomization. Okay. Now, when we are going to go ahead and talk about it, so these are the definitions that you have to go ahead and know to be able to answer the questions. Now, when we go ahead and we talk about it, okay, one correction. Over here, I said that the temperature will be 293, it's 298. Just wanted to correct that. Okay, the standard conditions are that this is going to be our pressure, okay, 101 kilopascal or 1 atmosphere, and the temperature is 298 kelvins. When you take 25 degrees centigrade and you add it to 75, so you get 298. All right. Now, these are the standard conditions that are going to be present. Now, there is another formula for enthalpy change, for not for enthalpy change, for heat energy. Okay. There is another interesting formula for heat energy that, again, you would have studied in your previous years. What's that formula? The formula is, again, this is a formula for heat change, heat energy calculations, right? So heat energy calculation, another formula that you can use for heat energy calculation is Q is equals to MC delta T, where Q is your heat energy, M is your mass, right? C is your specific heat capacity, and delta T is the change in temperature. Now, what you can do is that if you take the Q, if you take the heat energy you have calculated and you divide it by the number of moles, you will be able to calculate the enthalpy change. Okay. So if you want to calculate enthalpy change, all you have to do is divide the heat energy by. Now, these were some basic definitions. Talking about this topic, how are you actually going to be seeing the questions in this topic? Or what kind of questions are they actually going to be asking you in this topic? When you talk about your enthalpy change, there's a problem with enthalpy change. What's the problem that we see with enthalpy change? The problem with enthalpy change is that if I have a certain reaction and I want to calculate the heat energy change, So I will need to either use this formula, Q is equals to MC delta T, right? Either I will have to, like you guys did in IGCSE physics, you guys will have to do an experiment. You guys will have to take your solution, put it in a styrofoam cup, note down the increase in temperature, do the calculations and all that. Either you can go with the experimental route, right? That's what you can do. Or you need to somehow calculate the enthalpy of the product and the enthalpy of the reactant and subtract the two of them. You only have two options. Those are the only two options you can use to calculate the enthalpy change of any reaction. Either use Q is equals to MC delta T, put the solution in a insulated cup, add your reactant, note down the change in temperature, and do the calculations. Or go ahead and calculate the enthalpy of the product and enthalpy of the reactant. But there is a problem with certain reactions. You can use these methods for most of the reactions, but there are some reactions that will not work no matter what method you're using. Whether you decide to use Q is equals to MC delta T, or whether you decide to go ahead and utilize enthalpy change formula. Whatever method you're using, you will see that there are certain reactions for which it is very, very hard to calculate what the enthalpy change is, right? For example, if you're going to go ahead and talk about it, I told you the enthalpy change of hydration. It's very difficult to calculate the enthalpy change of hydration. Why? Because it's not easy for me to know what is the exact amount of water I need to add. I need to add to turn my anhydrous salt into hydrated salt, right? If I add too little water, I will not get the complete product. If I add too much water, it will dissolve and turn into a solution. So what's the exact moles of water that I need to add to take it from an anhydrous to a hydrous, right? I can't know how to do that. Since I don't know how to do that, so calculating the enthalpy change of this reaction would be really hard for me. I can't do it inside the laboratory easily at all. So what do we do in situations where we cannot directly calculate the enthalpy change? What if we have a situation where you and I cannot directly calculate the enthalpy change of any solution? So for that, we use something that is known as Hess's law. First, let me define Hess's law to you, and then I will actually explain to you what it is all about. Hess's law basically states, this. The total enthalpy change, in a chemical reaction is independent of the route by which the chemical reaction takes place, as long as the initial and final products are the same. Very complicated. It seems a bit confusing. What is he trying to say? So this guy Hess basically is the one who came up with this rule. What he actually stated was, okay, so let's go ahead and take an example. Let's say that I want to calculate the enthalpy. Okay, we were taking an example of enthalpy change of hydration. Okay, so I told you an enthalpy change of hydration. Let's take the same reaction that we discussed previously. I told you guys the problem with enthalpy change of hydration is what? That you don't know what is the exact amount of water you need to add, turn it from a hydrous salt to a hydrated salt. So it's really hard to calculate the exact enthalpy change. Now, I can take my reaction and instead of directly measuring this, instead of directly measuring what the enthalpy change is going to be, I can perform a series of experiments that will allow me to do the same thing. What do I mean by that? So I cannot do the direct measurement of this reaction. I can't directly take my sodium thiosulfate and add it in water and get my crystal, right? I cannot do this directly. So instead, I can perform two reactions. Okay? I can perform two reactions like this. What if I don't know how much water to add in the solution? Okay? I don't know. I don't know how much water I have to add to turn it from a hydrous salt to a hydrated salt, right? What do I do? Why don't I simply start by taking my by taking my sodium thiosulfate and adding water to it, right? Just add water. Doesn't have to be a specific amount of water. Let's just add water to it. What will happen? I told you if we add too much water, what's the problem? We won't I won't get a salt. I will simply end up getting a solution. So I will end up getting a solution of sodium thiosulfate, aqueous, a solution. Now this enthalpy change I can calculate. I can go with whatever method I like. I can go for Q is equals to MC delta T, and I can simply calculate what is the enthalpy change. I can name this enthalpy change of solution. Why? This enthalpy change of solution is the enthalpy change when 1 mole of solute is dissolved in a solvent, right? So I'm dissolving 1 mole of sodium thiosulfate. So I'm getting a dilute solution. So I can measure this. Okay. So I've taken my reactant and I put the sodium thiosulfate and the water together and I calculated the enthalpy change. Okay. Now, what did I do next? Then I took my crystal. Okay. I took my crystal and I also added water to it. I took my crystal and I also added water to it. What will happen? The same thing as before. You will end up getting a solution. Now, what I can do is that I can measure the enthalpy change of these two reactions and then calculate the enthalpy change of the reaction that I actually want. Let me make this make sense. Let's actually go ahead and talk about it and make it make sense. Because right now, I'm pretty sure you guys are very confused. How is it that we can do these two reactions and calculate the enthalpy change for hydration, right? Now, let me go ahead and draw this out for you. This is my sodium thiosulfate. I need to add water to it. So I can go ahead and get a salt. Now, this is the direct route of the reaction. The direct route is that I take my reactant, I react them together, I get the product. That's the direct route. What is my indirect route? Why don't I go ahead and take my sodium thiosulfate and water, and I don't need to worry about making a crystal. Why don't I go ahead and make it into a solution? Why don't I make a solution of sodium thiosulfate? This will be what? Enthalpy change of solution, because I am dissolving one solute into my water. Now, what else can I do? I take the crystal and I can also dissolve it in the water. And this will also be the enthalpy change of solution. This will be enthalpy change of solution of what? Of sodium thiosulfate, the anhydrous salt. What will this be? The enthalpy change of sodium thiosulfate crystal. So I can take both of them and I can dissolve them in water and I can make a solution of sodium thiosulfate. How does this make things easy for me? I can easily find out the enthalpy change of solution of both of them, of the crystal, of this hydrated salt, as well as the anhydrous salt. right? I can calculate the solution of the enthalpy change solution very easily. I can go in the lab, I need to make an infinity dilute solution, no problem. Add a large quantity of water, dissolve the solute, get the enthalpy change, right? So I can calculate standard enthalpy change of both the reactant as well as the product. Now, take a look. In my reactant, what is happening in this particular reaction? I am reacting the product with the water and the reactant with the water. What is the ultimate result? The ultimate result is that my final product is the same, right? Now, what I can do over here is that I can then use these values to calculate the enthalpy change of the reaction because I have the enthalpy change of the solution, right? And I have the enthalpy solution for the crystal as well. So I can use the enthalpy change of the salt. I can use the enthalpy change of the solution of crystal, and I can add and subtract them as needed depending upon what diagram you're making. Depending upon that, you can calculate the enthalpy change of hydration. How can I do that? Remember this. We're always going to be looking at those arrows that are head to tail. What does that mean? That means if we take a look, these two arrows are not head to tail. This is the tail, this is the head, and this is the head. They're head to head, right? So I'm not going to be looking at these two. Instead, so I'm not going to be looking at these two. Okay. What if I decide to take a look at this arrow and this arrow? Again, you can see they're tail to tail. They're not head to tail. So I won't take these two arrows. What about these two arrows? These two arrows are head to tail. This is the head of the arrow and this is the tail of the arrow. These two arrows are head to tail. Those arrows that will be head to tail, you will add them. So what are you going to write down? You're going to write down quite simply the enthalpy change of hydration. This is what you want to calculate. Plus, now this is enthalpy change of solution. Enthalpy change of solution of what? Of the crystal, of sodium thiosulfate crystal. So these are the two, this value you have. You have the enthalpy solution of sodium thiosulfate crystal. You don't have the enthalpy change of hydration. You have to calculate it. These two arrows will be added up and they will be equal to the third arrow. So our third arrow is enthalpy change of solution of the anhydrous salt, N2S2O3. Now, the enthalpy change of solution for both of these, for example, are given to you in the question. So they have, for example, told you that the enthalpy change of solution is, for example, over here, minus 7.6 kilojoules per mole. And over here, they've given you the value of plus 47.4 kilojoules per mole. All you have to do is put all these values in the equation. This equation you guys will have to make each time by yourself. It's not a fixed equation. You guys will have to figure out the equation for all the different reactions given in the exam. So I want to calculate enthalpy change of hydration. My enthalpy change of solution of the crystal is going to be plus 47.4. This is equals to enthalpy change of solution of the anhydrous salt, that is minus 7.6. So I will simply rearrange the equation. So I will do minus 7.6 minus 47.4 and I will end up getting my answer as minus 55 kilojoules per mole. And that's it. I have solved the question. I have managed to figure out the enthalpy change of my hydration simply by doing a series of experiments. So I could not measure the enthalpy change by the direct route. I could not directly take my salt and I could not directly dissolve it in water to calculate the enthalpy change. It was too complicated. It was not possible. So I said, instead of going through the direct route, why don't I go through some indirect route? Why don't I reach the same place? Because my goal is to reach the same place ultimately. That's my final goal. To be in the final place has to be the same. As long as my final product is the same, over here, what was the final product? The solution. As long as my final product is the same, I can calculate different enthalpy changes and I can add and subtract to get the enthalpy change of the reaction. And that's what I did. I said I will take the product, turn it into a solution. I will take the reactant, turn it into a solution. And I can calculate this enthalpy change I can measure. I can measure the enthalpy change of solution, no problem. So I cannot measure the direct enthalpy change. So why don't I measure it indirectly? Why don't I measure the enthalpy change to turn both of these into a solution? The final product has to be the same. That's the only criteria. If the final product is the same, what does that mean? I can simply indirectly calculate the enthalpy changes and add and subtract them, and I will be able to calculate the enthalpy change of the reaction. And this is what Hess's law states, that it is independent of the route. It doesn't matter whether I'm using the direct route or whether I go indirectly. Am I directly reacting the reactants and getting the product, or am I getting the same product but in different series of reaction? Right? It doesn't matter what do I do. Do I perform multiple small reactions and add up the values, or do I do it directly? It doesn't matter. All that matters is that the initial and the final product are the same. As long as your initial product and final product is the same thing, it doesn't matter whether I do it directly or whether I do it in small steps. My answer, my enthalpy change will be correct. And that's what you and I can see over here as well, that the total enthalpy change is going to remain the same. If I cannot measure the reaction directly, the enthalpy change of the reaction directly, no problem. I will perform different reactions in different steps and calculate their enthalpy change and get the answer. So this is what Hess's law is. And this diagram I've just drawn in front of you, this is known as Hess's triangle. I know this is initially a bit confusing, but don't worry. This actually is, once you actually get the hang of it, this is pretty easy and pretty simple. Majority of the time, the questions are easy to understand. The data will be provided to you in the questions. All the values will be given you in the questions. And the values will really help you out in making the triangle. Okay? Is this making sense? I know it's probably not making that much sense, but is this somewhat making sense? Is it a little bit clearer what it actually is about?
Yes.
Okay. Even if it's not clear, it doesn't matter. We are going to be looking at a lot of example questions on this. I'm going to go over a lot of example questions with you guys on this, and you guys will get the hang of it. So even if it's not making sense, which I don't think it's making sense to anyone, but you guys will get the hang of it, no problem. Okay, so what we will do is that we are going to go ahead and stop it over here for today. And inshallah, in the next class, we will go ahead.